Hello, I'm Daniel Lee, and this is my video report for Lab 3 Black Hole for Physics 2211. The purpose of this lab is to determine the mass of a black hole through reasoning from a star's orbit and subsequently find the initial velocity of a spaceship that can avoid contact with the black hole or planet. Here are three important aspects of my video that I'll discuss today. Firstly, Newton's second law, also known as the momentum principle, plays a major role in this lab in calculations. The change in momentum over the change in time is equal to the net force, which can be split up into parallel and perpendicular components. The third line notes the formulas. Additionally, velocity and position update will be useful for the lab's motion calculations. Universal gravitational force is an attractive force found through the following formula. It is derived from Newton's law of universal gravitation and is used to calculate the net force acting on the systems within the lab. As for the results, I found the mass of the black hole to be 1.33288 times 10 to the 34 kilograms, and the V initial of the ship to be -1 times 10 to the 7th for the X, and 2.5 times 10 to the 7th for the Y component in meters per second. These are some important principles that I'd like to discuss and expand upon. Firstly, within Newton's second law and the momentum principle, the parallel component is used to determine changes within physical speed and whether it speeds up or slows down. The perpendicular component is used to determine changes in the direction of motion. An important note of the universal gravitational force within the lab is that it is a non-constant force as the system travels in orbit around the surrounding. Thus, for the position update, V average is estimated to be V final. This is the method of process that I use. First, I establish our process by looking at Newton's second law and applying appropriate ideas. And then again, within the code, I change the values and apply the ideas to calculate net force, mass, and initial velocity of corresponding components. Third, I analyzed the results and answered our questions. Here are my initial conditions for the code to find the mass of the black hole. The system is determined as a star and the surrounding is the black hole. Within this part of code, the initial conditions are set. For example, gravitational constant is set to the appropriate amount, mass is previously given as 2 times 10 to the 30 kilograms, and delta T is converted to seconds as it is originally given as 1 day. Here's the code I utilized to calculate the mass of the black hole. First, I found the initial and final momentum of the star through mass times velocity calculations. Delta V and delta P were found from the previous values of initial and final momentum. dp/dt was found by delta P and delta T, and then I set Fnet equal to dp/dt by Newton's second law. I found the parallel component, which governs how the system speeds up or slows down, using the formula d times mag p/dt times p hat. I found the perpendicular component, which uses the direction, and I used the manipulation of Newton's second law from the other momentum principle to find it. Both components are set equal to the corresponding force components through Newton's second law. Lastly, I manipulated the universal gravitational equation to calculate the mass of the black hole. Here are the results of my code. Fnet, F parallel, and F perpendicular are given along with the orbits and its subsequent parallel and perpendicular force arrows. I averaged the black hole mass over the path and received it to be around 1.33288 times 10 to the 34 kilograms. Here are my initial conditions for the ship calculations. The system is the ship and the surroundings of the planet and the black hole. The black hole mass is found from the previous code, 5 constants are given, and the initial conditions are found through guess and check and ensures the ship doesn't crash. Here's the code I used to calculate the net force and thus the motion of the ship. R for each segment is found by using R system minus R source. R hat is then found by dividing R by the magnitude of R. Force is found through universal gravitational force formula. Fnet is equal to the total sum of forces on system by surroundings, and the movement from position and velocity update equations from Newton's second law to update the position and velocity of the planet and the ship. Here are the results of my ship code. The planet's orbital speed is given as 9.45 to 0.002 times 10 to the 6 meters per second, and its period is 1.8469 hours. It was 2.75582 times 10 to the 11 meters away from the black hole. Thus, the initial velocity conditions of minus 2.5 times 10 to the 7 for the x component and 3.5 times 10 to the 7 for the y component are satisfactory. Some sources of error could result from rounding for both the black hole mass and ship initial velocity, as it could lead to errors and skewed data. And the initial velocity I used could have definitely been off in terms of specifics. So the what does it mean question asks about the difference between the net force and the rate of change of momentum in terms of their parallel and perpendicular components. The change in momentum of the change in time is equal to the net force by Newton's second law. Thus, though they are technically equivalent values, the process to find either differs. Net force requires additional variables such as mass of the black hole and star for complete calculations. Rate of change of momentum can depend on simply the data of the star, as seen in part 1 of the lab when we calculated change of momentum with initial and final momentum. The what-if question asks how the initial velocities should change in order to enter an orbit around the black hole while still fulfilling the requirements of the original simulation. I found that an initial velocity of minus 1.45 times 10 to the power 5 and 1.34 times 10 to the power 7 for the x and y component, respectively, in meters per second satisfied these requirements. The velocity seemed to depend more on the y rather than the x component, as it should focus more on an upward motion. This differs from the simulation as it focused more on a horizontal motion. Thanks for listening.